Hello, everybody. Today we're going to get into chemistry and matter, and we're going to talk a lot about energy. So I'm going to turn on the little pointer here, and let's get started. All right. So when we talk about macroscopic world, this is the stuff you can see. So you can see an ice cube, right? That is the macroscopic world. On the other hand, in chemistry, we're really more concerned with what's happening on the particulate level. So this is the stuff that you can't see. Even with your standard microscopes, you can't see what the particles in the ice look like. So we tend to use symbols to describe what's happening in our world of chemistry. So here's something you've probably seen before: solids versus liquids versus gases. So in this solid, these little balls represent the particles that make up this solid. Notice they're very close together. They're not moving around much. They're just sort of like vibrating in their spots, right? Now, if we add more energy to it, let's say we heat it up, right? Then those particles might have more energy, might move around a little faster. Now they can slide past each other. Now we've got a liquid. The more energy you add to it, they might even break off and become a gas, where they're completely independent of each other. So solids, liquids, gases, it's really just about the amount of energy that the particles have and how quickly they're moving. So energy is the capacity to do work or produce heat. Hopefully you learned back in freshman year when you talked about physics, work is the capacity to move an object over a distance against a resisting force. So when I stand up, I'm working against gravity, right? I am moving this object that is me against a force. That is work. And that work takes energy. I need energy to stand up and walk around, right? So what are some sources of energy? Where do I get my energy from? I get my energy when I eat my breakfast, right? If I had cereal for breakfast, where did that energy come from? It came from the grains that were in it. Where did the grains get their energy? They got their energy from the sun through photosynthesis, right? So 3 types of energy that we're going to talk about here. 2 of them you probably really have heard a lot about: kinetic energy and potential energy. So back in freshman year when you were talking about physics, probably talked about kinetic energy and a roller coaster. So you're coming down the hill, going faster. That's the energy of motion. Potential energy was like when you were up at the very top of the hill. That was your stored energy. In chemistry, though, not only does kinetic energy mean machines moving, but it's the thermal energy. So we talked about those particles moving faster. Those moving particles have kinetic energy. On the other hand, the potential energy, that's stored energy. So like the water in a water tower, stored, right? In chemistry, we're also going to have stored energy in food and fuels. That's going to be like chemical potential energy. It's the makeup of the bonds is storing that energy in the gasoline in your car, right? Electrical potential energy could be because of difference in charges, like in a battery. So that's stored energy too. Now the last one, maybe you've talked about, maybe you haven't, but radiant energy is the energy in light. So when the sun sends its little light waves down here, it's got a lot of energy in it. That's the energy that runs the earth, right? We get our plants live with that energy. Sometimes it's too much energy if you get, skin cancer from some of the light from the sun. So let's talk about how we're going to measure it, and we're going to be doing some math and calculations here. So first of all, calorie is the common unit used to measure energy. Now you might think, oh, calories, I know what calories are. You do. You've heard about calories with food, but really the calorie that is on your food labels, that is really a kilocalorie. It's 1,000 little c calories. So if you see calorie with a little c, that is a chemistry calorie, and it's equal to the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So if I have 1 gram of water and it's at 20 degrees and I want it to be 21 degrees, I'm going to have to use 1 calorie to make that happen. If it's at 20 degrees and I want it to be 22 degrees, it's going to take 2 calories to raise the temperature of that 1 gram of water 2 degrees Celsius. Now, if I have 2 grams of water and I want to raise the temperature 5 degrees, I'm going to need 10 calories. So think about this, and your body is a lot of water, right? And we're warm-blooded mammals, so we're always trying to keep our temperature up. So that's why we need a lot of calories to keep our bodies warm and do all the work that our bodies do. Now, that is why we use calories with a capital C for your food labels, because nobody wants to know that that Snickers bar that has the, like 250 calories on it is really 250,000 calories. But we don't want to put that on the label, so we use kilocalories. So if you see capital with a capital C calorie, that is a kilocalorie. Now, the other term, the SI unit for calories, is the joule. And a joule is about the amount of energy required to lift an apple 1 meter. So if you take an apple and you lift it up against the force of gravity for about a little over 3 feet, that'd be a meter, that's going to burn 4.184 joules of energy. So you just burned a calorie. So if you did that, 250,000 times, that would burn off that Snickers bar you just ate. We're going to do some math. Okay, so we're going to do some math problems. I'm going to start with this first one, and I'm going to leave the other two for you to do, and there'll be a thing to turn in after this with those problems on it. But let's look at the first one here together. So a student uses 30 joules. Now, note that decimal. That's important. That decimal makes this a significant zero. So I got 2 significant figures. It's not just around 30 joules. It's exactly 30 joules. So that means my answer to this problem should have 2 significant figures in it. And she's putting the books on the shelf in the classroom. Convert this amount of energy from joules to calories. So 30 joules, and we're going to calories with the small c. So if I go back here, I'm like, okay, 4.184 joules is 1 calorie. Now, you're going to have to bear with me here. I'm going to try to use this Jamboard to write, but I'm not great at writing on this little board and making it show up on the computer. So let's see. We always want to put what we're given right here. So let's see if I can write. Hold on. I'm going to get this. Get better. 30. That's a 0. And joules. All right, so I got my 30 joules over there. Perfect, right? Since I have joules over here, I need my joule term down here. So my conversion factor was 1 calorie is 4.184 joules. Okay? And up here, I need my calorie term. That's what I want. So 1 calorie. Now, my joules are going to cancel, right? Cancel that. And now I just have to do the math. 30 times 1 is 30, and then divide that by 4.184. I'm going to use a calculator for that. I got 7.170172, but how many significant figures do I need? Remember, there was a little decimal point there, which I don't think I really showed very well. And so I need 2 significant figures. So that's going to equal 7.2. I'm getting better. Calories. Got to put your units, right? Hey, I got a little better towards the end. Practice, practice. So that's how you would work out that problem. Don't forget, your answer to be fully correct needs to have the right number of significant figures and a unit after it, as well as being calculated correctly. So let's go back here. All right, pointer. So when I look at this one, you've got 135 calories, and you're going to be turning it into joules. So it's basically the opposite of what we just did. Now this one is going to be got 17, notice the capital C, those are food calories, and you want joules. So you're going to have to first turn the food calories to regular calories, little c calories, and then turn those into joules. So we'll give you a chance to do that here in a little bit. But let's talk a little about of law of conservation of energy. So the law of conservation of energy and matter is what it really is energy is not created or destroyed. It just changes from one thing to another. So the energy that you got from the food you ate this morning, you're using now to do your homework, watch these videos, move things around, walk around if you need to. And then the energy that you have, you're using to put into other things. The energy from the food came from, well, depends on what you ate. If you had some bacon, then the pig got its energy from the food it ate. And if it ate corn, let's say, the corn got its energy from the sun. So it's just a big cycle. Now another cycle here, this is the CO2 cycle. So you may have remember this from biology, right? So animals are exhaling CO2, right? Inhaling oxygen. Plants are doing the opposite. They're taking in the oxygen and, taking in the CO2 and letting the oxygen out. And so it's this nice little balance. And for a long time, we had just a nice little balance going here. If we burned, let's say if humans wanted to keep themselves warm and they burned a tree, well, that let off CO2 as a combustion reaction, but that CO2 would get taken up again when you grew a new tree, right? It would become part of the new tree. So it was a nice little cycle we had going. But then we started finding new sources of CO2 down that were been buried inside the earth for, millions of years. And we've dug them up, started burning them and putting them in the air. So we have been using fossil fuels, which is natural gas, coal, or petroleum, to use as energy for quite a long time. Now, the problem is these things were trapped down inside the ground. Okay, so a lot of carbon in there. And now that's a lot of carbon that when we burn it combines with oxygen to make CO2 and puts it into the air. So it used to be trapped underground. Now it's up in our atmosphere. The other problem, of course, with these things is we're not making any more of them. Earth isn't, replenishing its petroleum or natural gas or coal reserves. So once we use these, they're gone. So it is incumbent on us to figure out new ways to produce energy because these are going to run out. We are kind of addicted to our energy. If you can live, a day without electricity, it would probably be difficult for you. You're like, my stove doesn't work. I don't know how to cook any food. So that could be a problem. If you've ever had your power go out for a week, like back in 2008 and 2009, we had that windstorm and that snowstorm. Any of you that tried to live without power for a week, it was probably quite a challenge. So we want to keep having energy sources. So this is back in 2007. You can see back then we had only 7% of our energy was coming from renewables and about 8% from nuclear power. This is the US, by the way. Now, 2019, so a little bit later, not much later, we haven't changed too much. We use a little bit less petroleum. We use a little bit more natural gas. We use a lot less coal. So there's a lot less coal being burned and dug out of the ground. Again, there's only so much of it there, so it becomes more and more expensive to get it out of the ground. We're not going to mine it as much. The nuclear power, notice no change there. We haven't really built any nuclear power plants in the past decade, well, several decades, because people are kind of, it's got a bad reputation. On the other hand, renewables, look at how things have kind of changed here. So Back in 2007, only 5% of our renewables were coming from wind, whereas now you've got like 24% coming from wind. So you might have noticed wind farms popping up around the country as a way to make energy, and that's a renewable thing. We're always going to have wind, right? There's less use of biomass as we've kind of turned to other things. Biomass still, when you're still burning it and releasing CO2, so it hasn't been the most popular, although biomass and biofuels, if you put them together, is kind of different. Well, actually, maybe they've got wood here too, so that's kind of a biofuel too. So I guess if you add all those up, it's pretty similar. The hydroelectric kind of gone down a bit. Solar's gone way up as we've gotten cheaper solar panels, easier to install and use. So solar's gone up. So again, we're looking for some more renewable resources that we won't run out of. So just a little thing there. So the energy crisis, that's what's happening. We have fossil fuels are going to run out. There is only a limited amount of them. There will be a day where people don't have them anymore. So what are we going to do? Just stop using electricity? Don't think so. So they're limited. Look for more renewable forms. As well as we could also get into the CO2 climate change, but that's for a little bit later when we get into the chemistry of the reactions. Oops, backwards. Here we go. So the last thing I want to talk about is how to measure temperature. So we don't really use Fahrenheit. If you wanted to measure something in Fahrenheit, you would have to use this formula to translate it to Celsius. So in science, we tend to measure things on the Celsius scale for the most part. Celsius, we say, hey, what point does water freeze at? Let's call that 0 degrees. Where does it boil? Let's call that 100, and just divide them up into increments in there. So, but the problem with the Celsius scale is you have negatives, and there are some times where we don't want to have negatives. So, especially with math and some of the gas laws, we can't really use negative numbers, sort of make the equations go crazy. So, we needed something that had an absolute 0, no negatives. So if water freezes at 0, we said, well, what's the point where everything would be frozen? And we extrapolated that down to what we call absolute 0. And that would be on Kelvin, that is negative 273 degrees Celsius. So the degrees of Kelvin and Celsius are the same. So if you go up 1 degree Kelvin, you go up 1 degree Celsius. So the only difference between the two is Kelvin is always 273 degrees higher than Celsius. So if you measure something in the lab in Celsius on the thermometer and you want to convert it to Kelvin, you just add 273. If you have something in Kelvin and you want to go to Celsius, you just subtract 273. It's that easy. So what is happening? How does the thermometer even work? What's happening? So let's pretend you got the old style thermometer here. Mom sticks it in your mouth and it puts a little bulb down in your mouth. It has these little particles in it. Well, the particles in your mouth are moving pretty fast because they're nice and warm. So they're going to collide with this thermometer and give that energy, same energy, to the mercury inside the thermometer. And as those particles move faster, they're going to move up the thermometer. So they got more kinetic energy, they're going to move up. So we're going to see the little mercury rise in the thermometer. So it's really just transferring that energy. All right, that is pretty much it for today. So you're going to have a little Google form where you can go back and answer these questions, work them out on a piece of paper, and then type in the answer for me. And good luck.